Okay, YouTube, in this video I'm going to graph another rational function, but kind of pick up the pace a little bit in this instance. So we'll run through our steps here that we want to be getting used to, but basically what we're always going to do is this. We're going to find our x and y intercepts, find the asymptotes, and then plug in some extra values and basically sketch our graph from there. So let's start by simplifying this expression if at all possible. I certainly did give us an expression that can be factored on top and bottom. So we have x plus 2, x minus 1 on top. On the bottom here it looks like x minus 3, x plus 2. So in the first case here, we want to make sure that we cancel out any common factors. We say that our rational function is really x minus 1 over x minus 3. Okay, so let's start by finding our y-intercept. That's always the easiest one to find because really what we're doing then in our table of values here is we're plugging in 0 for x. To find the y-intercept, we plug in 0 for x. And in this case, you can see that if we plug in 0 for x, we're going to get a positive 1/3 because really this would simplify out to be 0 minus 1 over 0 minus 3, which is a negative 1 over negative 3. We would get a third. So we would say 1/3, and that is a point that I'm going to go ahead and stick on our graph. It'd be right about here. So now that we've found our y-intercept, what we want to do is find our x-intercepts. So to find an x-intercept, recall that what we're doing is we're setting that y value equal to 0 here in this expression. So let's start getting used to this, but basically when you set a rational function equal to 0, the only way this happens is if the top is equal to 0. And in this case here, I can see that this top part right there is going to be equal to 0 if and only if x equals 1. So we would say when we plug in 1 here, we're going to get a y value of 0. And we could say that that is also an intercept of our graph. So now that we have these two intercepts, let's work on getting our asymptotes here. So first one we always find is find the vertical asymptotes. That's because we set the denominator expression equal to 0 to find this. Remember, a vertical asymptote only occurs where our graph is undefined. So if I were to say let's set x equal 3 or x minus 3 equal to 0 and solve this, then we would determine that x equals 3 is where we have a vertical asymptote, and it'll be our only one. And then as far as a horizontal asymptote is concerned, now we're looking at the degree. So the degree of the top and the degree of the bottom, I notice that they are the same in value. So we'd say since it's balanced, then our horizontal asymptote is at the ratio of our leading coefficients, 1 over 1, or in this case at 1. So we have two asymptotes. We want to make sure that we put these on the graph. So we say x equals 3. We'll go ahead and go over here to x equals 3, and we'll put this vertical asymptote on there and make sure that we label it x equals 3. And then you can go ahead and start to put on y equals 1 as a horizontal asymptote on our graph as well. This value that our graph is going to get really, really close to on its ends. So we say y equals 1. So now that we have these, basically, we're going to find at least 2 points per branch of this hyperbola, and that just means that we're going to plug in two x values to the left of and to the right of every vertical asymptote. So in this particular case, since we plugged in x equals 3 and get it undefined, we're going to plug in two values to the left of this and two to the right. Now I notice that I don't have to do it positive 1 because we already found that that is a 0. So we can plug in positive 2. We can not plug in 3, but we can plug in 4 and 5. And we're actually just going to need to find some values here. So we have f of x is this x minus 1 over x minus 3. So let's go ahead and start by plugging in 2. On top here we're going to get 2 minus 1, which happens to be 1. And on bottom we're going to get 2 minus 3, which is negative 1. So it looks like we get a y value of negative 1 here. For 4 we get 4 minus 1 on top, which is 3. Oops, 3. And we get 4 minus 3 on bottom, which is 1. So this will be at a height of 3. And then at 5, we get 5 minus 1 on top, which is 4. And on bottom, we get 5 minus 3, which is 2. So we get a height of 2. So now we're just going to go through and graph all these points. We say 2 comma negative 1, starting at the origin. We'll go right 2 and down 1. It looks like that fits the pattern here where this left branch is going to be. On the right side, we would say 4 comma 3. We'll go right 1, 2, 3, 4, up 1, 2, 3. That'll be at this height. And then we'd say that 0.5 comma 2 is also on our graph. That'll be this right here. So you can see how this will provide us with enough information to say, well, out on the end there, our graph is getting really close to that horizontal asymptote. And then as we approach the vertical asymptote from the left, it looks like our y values must be decreasing to negative infinity. Same thing on the right. As we go way out to the right, our graph is going to get really close to that horizontal asymptote. But as we come into the vertical asymptote from the right side, our y values approach positive infinity. So the last thing we want to do here is denote or indicate domain or range. And I notice that domain, it's going to be all values except for those that were undefined, which is x equals 3. So we can say our graph starts way out on the left at negative infinity and goes up to but doesn't include positive 3 here. And that is in union with 3 out to infinity. starts up again just after x equals 3 and goes on forever and ever. And in the range, it looks like we hit all y values except for we never crossed the y value of 1. So in this particular instance, we would say that our range is basically from the bottom up to a height of 1, not going through 1, starting up at 1 again, whoops, and then going up to infinity.